All right, folks, we are going to just kind of give you a rundown real quick. We got 10.4 to do. We'll then jump to 13.1 because it's like there's a little bit of a jump between sections that deal with hypothesis testing. So 13.1 will take us into another type of hypothesis testing. And then we'll come back and do, I think, 3 sections out of Chapter 12, which lines of regression and correlation and that kind of stuff. Which is not directly compare. I mean, it's related, but it's not. It'd be kind of a different or new topic. So, but we're almost there, almost finished. The topic we'll talk about today, and probably through at least midweek, is talking about testing the difference between two proportions. Okay. The idea is, if I have, 200 people in one population, and we look at maybe 30 of them for whether they're left-handed or right-handed, okay, and we get a certain percentage, okay, or proportion, and then do that with another population, okay. Maybe we do it with like seniors, and then maybe we do it with freshmen, and we look at a sample, let's say instead of population 200, let's say a sample of 200, and we get like 30 of them to be left-handed out of the seniors. And then we take another sample out of the freshmen, and maybe that sample is 150, and we look at it and say, okay, well, there's 21 of them that are left-handed. Can we talk about the populations being different or the same? Does that make sense? Okay. So it's that idea. We've got that binomial situation going on where you can either be left-handed or right-handed. You can only be one of the two. Fixed number of trials. We got independent samples. Okay. So there's some criteria that has to be met before we do a hypothesis testing on the difference of two proportions. That stuff's listed here at the beginning. The one thing I want to make sure real quick, and this is what I was trying to fix at the beginning. Okay, so some of yours, and it didn't fix everywhere. Every once in a while here, you're going to see, like you see here is P bar, right? Okay, down here, you see where it's P bar, Q bar, but you see right here where it says PQ. For whatever reason, when I input this in, I input it this way in Microsoft, but it keeps saving like this. So I don't know why that's doing that. Does that on your guys, anybody print this out and see the same thing? Okay. So anything that has that bar underneath, that bar should be on the top. So I apologize for that, but I don't know how to fix it. Says, so for testing the difference between two proportions, the sample proportions, okay, of success, which is called P hat, okay. If you remember this, P hat is X divided by N, okay? X is the number of successes that you are realizing, okay, the number of items or objects in your sample that align with what you're interested in, and N is the total number of individuals or objects in your sample, okay? So X over N is the ratio of number of successes to the number of trials in a binomial experiment, okay? That's ultimately the formula for like classic probability there, okay? So when we have two independent samples, we'll have two P hats, okay? So you have P hat sub 1, P hat sub 2, okay? And this is, maybe that's left-handed people in sample 1 divided by sample 1 size, and this would be left-handed people in sample 2 divided by sample 2 size, okay, if that's what we were interested in, checking left-handedness. So we will be interested in the difference between P1 and P2, population 1 and population 2. Therefore, because we won't have the information about both populations, okay, we will use P hat sub 1 and P hat sub 2, so proportion of sample 1 and minus proportion of sample 2. These three things must be true in every hypothesis test that we've done so far. There's been conditions that have to be met in order for us to actually use the test. Okay? All of them have had that. Samples must be randomly selected. Okay? If things are not randomly selected, then things are skewed, and the data that you get back, the results that you get back, are not accurate. Okay? Samples must be independent. Okay? And then because this is a binomial situation, we've talked about this multiple times. We talked about it back when we dealt with binomial distributions in Chapter 4, I think it was. We talked about it again in confidence intervals in Chapter 8. Did it with hypothesis testing of a single sample in Chapter 9, and now again in Chapter 10 when we're dealing with a difference of two proportions. N times P, if you remember, N times P had to be greater than or equal to 5, okay, for the distribution to be normal, okay, or for us to make the idea that the normal distribution can approximate this binomial situation. So what we have then is that N1 times P1. So when we're looking at sample 1, N1 times P1 has to be greater or equal to 5, okay, and remember P is the proportion and N is the sample size, okay? So that P1 is the, if we have, let's say, 100 people that are in the sample and 30 of them are left-handed, then 0.3 would be that P1. Okay, so that's the proportion that we're interested in. Q1, remember Q1 would be the complement then of that. Okay, so N1 P1 has to be greater or equal to 5, N1 Q1 has to be greater or equal to 5. And that's for sample 1, and then we have to do the same thing for sample 2. Okay, if this is true for one sample but it's not true for the other sample, you cannot do the test. You have to have true for both samples. So that's why we have N2 P2 greater or equal to 5, and N2, this should say Q2, N2 Q2 right there, greater or equal to 5. So that's something that they're going to probably be one of if we've got a question that has 3 or 4 parts, that will probably be part 1 to check to make sure that is satisfied. Okay. So if these conditions are met, sampling distribution for P hat sub 1 minus P hat sub 2, which is the difference between the sample proportions, is normal with the following mean. Okay, the mean would be P1 minus P2, and here's our standard error. And this standard error is similar to standard errors that we've seen in the past. Okay, so the idea is that sigma of P hat 1 minus sub P hat 1 minus P hat 2 is equal to this formula. Square root of P1 Q1 over N1 plus P2 Q2 over N2. Okay. If we go back through some of the other formulas that we've seen so far, that is similar to other standard errors that we've seen in previous tests. Okay. I believe when we did the Z test, this was sigma over N1, sigma 1 over N1, and this was sigma sub 2 over N2, or I guess it was sigma squared for both those. Okay, so it's very similar structure. Okay, so let's construct the different formats of hypotheses that can be created. Okay, so now because we're talking about proportions, we're going to use P instead of mu. Okay, so our null hypothesis, we're going to make the argument that, and much like when we talked about the difference between two means in independent samples, we said that there is no difference. That's the agreed upon assumption at the beginning, that there is no difference. Okay, so if there is no difference, then H sub A, and again, I don't know what's going on with the formatting in this. This was all correct in Word. This got moved, so I'll put it down over here. H sub A could be P1 minus P2 not equal to 0. Okay. We could have H sub 0, which is P1 minus P2 equal to 0, and we can have an alternative hypothesis that P1 is, let's just say P1 minus P2 is greater than 0. And we can also have one where it says it is less than 0. So H sub 0, P1 minus P2 equals 0. So those are the three different hypotheses, kind of structures that you're going to see. Now they could say, if we look at that first one where it says H sub 0, P1 minus P2 equals 0, well, if I add P2 to both sides, I get P1 equals P2, right? Okay, so proportion 1 equals proportion 2. And then on the bottom one, I could say that P1 does not equal P2. Okay, so because of the simple addition that we can do here, there are varying formats of this. Okay, there are varying formats of that, varying formats of that, just by adding P2 respectively to each side in those tests. Okay, I would argue that these are probably the ones that you're going to see most often. Okay, that's the way I'm going to write them. So since P1 and P2 are unknown, okay, so that's the proportion from population 1 and that's the proportion from population 2, those are unknown. A weighted estimate of P can be computed using the following formula, okay? So we call that P bar, okay? So what's going to happen is that we want to use P in our formulas for the test statistic, okay? But we don't know the entire populations that P1 and P2 are representing. So what we do then is it's called a weighted formula here, where they take N1 times P hat 1 plus N2 times P hat 2, and then divide that by the sum of your two samples. Okay, those are your sample sizes on the bottom. And that becomes P bar, okay? P bar is then the value that is going to be used in place of P1 and P2. Okay, it's the best estimate for those two things. Okay, Q bar then would be 1 minus P bar. Okay, so the above weighted estimate is based on the hypothesis that P1 equals P2, or that P1 minus P2 equals 0. Okay, says thus P bar is a better estimate than either P hat sub 1 or P hat sub 2. Does that make sense? Okay, so we don't have P1 and P2; those are unknown. Okay, P hat and P hat 1 and P hat 2 would be replacements for P1 and P2. Does that make sense? Okay, but I don't want to just say, well, P hat 1 and substitute that in for everything, or P hat 2 substitute that in for every P that you see. Okay, so we use a weighted average essentially between the two, and that is better than choosing just one or the other. Does that make sense? Okay. So substituting P hat 1 equals X1 over N1 and P hat 2 equals X2 over N2, and the above formula produces a simplified formula for P bar. So we can see this, right? So if we were to go in here and say, okay, well, P hat, which we've already talked about as X1 over N1, times then N1, what happens with those N1s? Cancel out, right? Okay. Right here, if I look at P hat sub 2, we said that that was X sub 2 over N sub 2 previously, and I have this N sub 2 out in front. What's going to happen with those N sub 2s? Cancel out, right? So really, if I make that substitution of those two things for P hat 1 and P hat 2, what I end up with is just X1 plus x2 in the numerator, okay, which makes our formula a little bit easier. So P bar, that formula right there, is going to be, calculation-wise, a little bit more convenient for you to use, okay? And remember, x1 plus x2, those are the values, those are the objects that align with the successes that you're looking for in your scenario. So if we're looking at like left-handedness, okay, that would be the amount of people that are left-handed in sample 1 and the amount of people that are left-handed in sample 2. And then N1 and N2 are the sizes then of those two samples. So again, because the standard error is based on knowledge of P, using the weighted estimate P, this should say P bar. Again, don't know why it's doing that. So that's P bar. And that's P bar, Q bar. Okay, so our standard error now, okay, is this formula that we're going to use inside our Z test. Okay, that's how we're going to standardize these data values. Okay, so just as before, you take your observed differences minus your expected, and our expected P1 minus P2, that's in our null hypothesis. That number is 0, is it not? Okay. And then here we're going to divide by our standard error. And that's the same way that we have standardized data values since day one. Once we have that information, then all the hypothesis testing that we do and that we have done is the exact same. Okay. Now we know we're using a Z-test here, so we use the normal commands in Excel, or maybe if we use StatCrunch or GeoGebra, we can use the Z distribution. Okay. So example says a medical research team conducted a study to test the effect of a cholesterol-reducing medication. At the end of the study, the researchers found that of the 4,700 randomly selected subjects who took the medication, 301 died of heart disease. Of the 4,300 randomly selected subjects who took a placebo, 357 died of heart disease. Okay? At 1%, can you support the claim that the death rate due to heart disease is lower for those who took the medication than for those who took the placebo? Okay? So hopefully this type of situation, a scenario, can explain or give you an idea of where this type of test would become significant or useful. Okay? What we want to do here is we want to talk about our null hypothesis first. Okay? And I think it's important, so I've already got the table down here for you. Okay? But to idea, if I call this P sub 1 minus P sub 2 is equal to 0, okay, it might be better, and I'm going to leave it as P1 and P2, but you might be a person that says P sub M for medication and P sub P for placebo, okay? That might make it easier to realize what was sub 1 and what was sub 2. But I've got those down here in the chart, so hopefully if we forget, we can at least reference back to the chart and say, oh, well, anything with a 1 as a subscript was the medication. Is that okay with everybody? All right. So a medical research team conducted a study to test the effect of cholesterol-reducing medication. It says, can you support the claim that the death rate due to heart disease is lower for those who took the medication? So we want P1 to be lower than P2. Does that make sense? Okay. Well, if I do subtraction, doesn't this mean that P1 minus P2 would be less than 0? Okay, so that's my alternative hypothesis, and it's the claim. So P1 minus P2 is less than 0. I think it's nice to have it this way because this tells you what kind of test it is. What direction is the test? It's a left-tailed test. Okay. So for the left-tailed test, we want 1%. It's a Z distribution. So let's find our critical value. That area, 0.01. So we're going to use Excel, and we are going to use the norm.inv. You might remember this value because we've used it so many times, but I think it's always best just to grab Excel. Equals norm.inv. Probability is 0.01. Mean is 0. Standard deviation is 1. And negative 2.32. Negative 2.32 is that Z value. Say Z sub C for the critical value. Okay? All right. Now we're going to find our standard score. Okay? So now that is P1 minus P2. Okay? It's actually P hat 1 minus P hat sub 2 minus then P1 minus P2 all over P hats, Q hats is 1 over N1 plus 1 over N2. Okay? That's exactly what this thing here is. And we have our information here. Okay? Now the nice thing is that they've already processed all the components that we need, okay, except for P bar and Q bar. But they gave me P hat sub 1, so 0.064, minus P2, P hat sub 2, which is 0.083. Okay, so that is that difference right there. And then you're going to subtract this from it, but that number, P1 minus P2, is this right here, correct? P1 minus P2 is 0, always 0. Now we're going to divide by, now we need P bar. Okay, so this is a value that we should maybe calculate on the side here. P bar is going to be x1 plus x2 over n1 plus n2. So if we take x1 plus x2, which is 300 plus 357, it's going to be 658, over then 4,700 plus 4,300 gives me 9,000, right? Okay, so figure out what that is as a decimal, 658 divided by 9,000. It's approximately 0.07311. That's P bar, okay? So Q bar would be 1 minus that. So let's just kind of clean this up a little bit. So P bar 0.07311, Q bar 0.926 0.9. And then times 1 over n sub 1, which is 4,700, plus 1 over n sub 2, which was 4,300. Okay. So I know there's some rounding here that I've done. I'm going to jump to Desmos and just see if we can maybe mitigate some of that rounding. All right, so we got P bar that we need. So I'm just going to call it for the mode, just because I don't know if I can do subscripts in here. Okay, that'll work. So that'd be P bar. I'm just going to say Q bar then is 1 minus P bar. Okay. So then when I type in to find my Z, so Z would equal 0.064 minus 0.083 minus 0. And we'll divide that by, so it's the square root of P bar times Q bar times then 1 over 4,700 plus 1 over 4,300. And that is then our Z test statistic, negative 3.458. So Z equals negative 3.4, let's say 6 for purposes of rounding. And where does that show up then in our curve here? Should show up in the rejection region, right? Okay, so that means we're going to reject the null hypothesis, which tells us then if we're going to reject that, then we must have evidence for this, which if we have evidence for that, through manipulation, we can see that P1 would be less than P2. Does that make sense? So our argument then would be that through the testing here, we have evidence to support that the population that took the medication, they do have a lower death rate due to heart disease than those who took the placebo. So what does that tell me as maybe a doctor, a physician, a marketer for this drug? It works, right? There's efficacy here, okay? So we can maybe start prescribing that, and it's at a 1% confidence level, so it's a pretty or 1% level of significance. So it's a we're 99% confident that that's the true conclusion. Does that make sense? All right. Now I know there's a lot there. Okay, there's a lot of P hats, P bars, Q hats, Q bars, N1s, X1s. We do have, if we look at StatCrunch, I believe, and I'll double check this. We'll start this with class tomorrow. We should be able to go to StatCrunch and just process this data, put it in, and it will spit back the same results to us. Okay. So my hope is that that's what we turn to, especially with these scenarios in Chapter 10, because there's 2 samples, so much to keep track of, so many calculations to do. I think using the tools that we have at our disposal is going to be of benefit. We'll start that tomorrow.